Hello students, today we are going to see how we can officially define the limit of a sequence and also how to calculate limits of powers and how to use comparison test to find the limit of a sequence. So first let's work out a question. The first question is A part. Write the first six terms of the sequence an is equal to n by n plus 1, where n is equal to 1, 2, 3, etc. Also represent the sequence graphically in two ways, and at the end find the value of limit n tends to infinity n by n plus 1. And in B and C, we have to repeat the same questions for different ans. In B, it is an is equal to minus 1 raised to n by n, and in C, and in C, an is equal to minus 1 raised to n by n plus 1. So, for solving the same, an at the first is given to be n by n plus 1. So we have to calculate the six first terms of the sequence. So A1 is equal to 1 by 1 plus 1, which is equal to 1 by 2. A2 is equal to 2 by 2 plus 1, which is equal to 2 by 3. A3 is equal to 3 by 3 plus 1, which is equal to 4. A4 is equal to 4 by 4, 4 plus 1, which is equal to 5, and A5 is equal to 5 by 5 plus 1, which is equal to 6, 5 by 6. A6 is equal to 6 by 6 plus 1, which is equal to 6 by 7. So we got A1, A2, A3, A4, A5, A6, and we are asked to graphically represent the same in two ways. So first we are going to represent the sequence from A1 to A6, the first six terms in the real line. So this is the real line. So here you have 0 0.5, 0 0.6, 0 0.7, 0 0.8, 0 0.8 marked. First we have to mark 1 by 2, which is equal to 0 0.5, and A2 is equal to 2 by 3 is mapped correspondingly. A3, which is equal to 3 by 4, which is 0 0.75 mapped here. A4 is equal to 4 by 5, which is mapped at 0 0.8. The same, 4 by 5 is equal to 0 0.8. A5, 5 by 6 is mapped correspondingly here, and A6 is equal to 6 by 7 will come somewhere here. Okay, so here we can understand that A1, A2, A3, A4, A5, A6 are going on like that. Okay, so this is how they are moving in the real line. The same can be represented in R2. So in order to represent that, we know that sequences are actually functions from natural numbers to the values we are giving. That means here the points will be plotted as 1 ordered pair 1 comma the first term A1. The second point will be ordered pair 2 comma A2, ordered pair 3 comma A3, ordered pair 4 comma A4, ordered pair 5 comma A5, ordered pair 6 comma A6. So here that will be ordered pair 1 comma 1 by 2, ordered pair 2 comma 2 by 3, ordered pair 3 comma 3 by 4, ordered pair 4 comma 4 by 5, ordered pair 5 comma 5 by 6, ordered pair 6 comma 6 by 7, and each of them are neatly plotted here in the second figure. So we have represented the sequence an, which is equal to n by n plus 1, both in R as well as in R2. So we have to now calculate what is the limit of this sequence. So we know that as n tends to infinity, the fraction n by n plus 1. See, you can see in the figure that you can check out in the real line here. The values are not exceeding 1. See, all the points are coming like this and it is not going above 1. So we can have a guess that the limit may be 1. That is just a guess. And we have to verify this guess. So we have to verify that 1 is the limit of the sequence an is equal to n by n plus 1. So for that, to say that 1 is the limit, you have to consider the difference 1 minus n by n plus 1. So this is a guess that this is the limit and this is our sequence an. So we are taking the difference between the guessed value for the limit and the sequence itself. So 1 minus n by n plus 1 is equal to taking the LCM, the denominator whole will become n plus 1 and you have to multiply n plus 1 here. So you get n plus 1 minus n divided by n plus 1. So you can cancel n and minus n to get 1 by n plus 1. So we know that as n is moving on to infinity, 1 by n plus 1 will approach 0. So this difference, the difference of 1 and n by n plus 1 will approach 0 as n tends to infinity. See, as n tends to infinity, the difference 1 minus n by n plus 1 is approaching 0, which means that the sequence an, which is equal to n by n plus 1, is approaching 1. Because 1 minus n by n plus 1 is approaching 0. That will automatically imply n by n plus 1 is approaching towards 1. Right. So we can say that limit n tends to infinity, n by n plus 1 is 1. So we are going to do the same things for the next question. An is given to be minus 1 raised to n by n. So we have to find the first 6 terms of the sequence. So you have a1 is equal to minus 1, a2 is equal to 1 by 2, a3 will be equal to minus 1 by 3, a4 is equal to 1 by 4, a5 is equal to minus 1 by 5, a6 is equal to 1 by 6. And we are representing the same sequence in two ways, on R as well as on R2. So the points are plotted in the real lines. See, A1 is equal to minus 1 is plotted here. A2 is equal to 1 by 2 comes here. A3 is equal to minus 1 by 3 comes here. A4 is equal to 1 by 4 is here. A5 is equal to 1 by minus 1 by 5 is here. A6 is equal to 1 by 6 will be here. And it is plotted neatly. And in the second case, we are representing the same sequence. An is equal to minus 1 raised to n by n on R2. So the points, as earlier said, we know it is they will be of the form ordered pair 1 comma a1, ordered pair 2 comma a2, etc. Ordered pair 6 comma a6. And here we have ordered pair 1 comma minus 1, ordered pair 2 comma 1 by 2, ordered pair 3 comma minus 1 by 3, ordered pair 4 comma 1 by 4, ordered pair 5 comma minus 1 by 5, ordered pair 6 comma 1 by 6. So we are plotting them neatly here. See, 1 comma minus 1 is plotted here, 2 comma 1 by 2 is plotted here, 3 comma minus 1 by 3 here, 4 comma 1 by 4 here, 5 comma minus 1 by 5 here, and 6 comma 1 by 6 here. So it is neatly plotted, right? And we are understanding that as in the earlier question, here the points were moving like this, going on, going like this, right? And here in this case it is going like this. What is here, then it is going up, it is going here, it is going up, it is going here, like that. Okay. And here also there is some difference when compared to the first question. Okay. Now as n tends to infinity, an is equal to minus 1 raised to n by n. We understanding that, see, it is moving closer and closer towards 0, right? Moving on like that. So you get limit n tends to infinity minus 1 raised to n by n is equal to 0. Also here in the real line, you can see that it is approaching from the left and from the right towards this value 0, right? See? So that means limit of this sequence will be, of course, 0. Now the third question is an is equal to minus 1 raised to n by n plus 1. So here a1 is equal to minus 1 by 2, a2 is equal to 2 by 3, a3 is equal to minus 3 by 4, a4 is equal to 4 by 5, a5 is equal to minus 5 by 6, a6 is equal to 6 by 7. And then we are going to represent the same sequence a1 to a6 in two ways on the real line as well as on R2. So when we are plotting on the real line, you get A1 is sitting here, A2 is sitting here, A3 will be here, A4 will be here, A5 will be here, A6 will be here, and they are moving like this, right? Okay, here. And what about on R2? 1 minus 1 by 2 will be the first point, the ordered pair. Ordered pair 2, 2 by 3 will be here. Ordered pair 3 minus 3 by 4 will be here. Ordered pair 4, 4 by 5 will be here. Ordered pair 5 minus 5 by 6 will be here. Ordered pair 6, 6 by 7 will be here. And we can see that it is moving away, right? It is moving like this here and it is moving like this here. So we can understand that the sequence is actually not approaching to a particular point, particular number. So from the figures, we can infer that an doesn't approach a particular number because some move closer to -1. See here, here you can see some are moving closer to -1 and some are moving closer to 1, right? So that is not the case. We need all of them to approach to one particular number. So we can uh, infer that an, the third sequence, an is equal to -1 raised to n, n by n plus 1 doesn't have a limit. Now to officially define limits of sequences, the sequence A1, A2, A3, etc. An is approaching a number L as a limit. We say that it is L is a limit of the sequence. If An gets closer and remains very close to L as N is becoming large. So this phrase, what we just said now, is denoted as limit n tends to infinity, An is equal to L. So that is a notation for the limit. So in precise terms, we can use an epsilon n definition. So limit n tends to infinity, An is equal to L. We are saying when is this going to happen? For every epsilon greater than 0, if for every epsilon greater than 0, if we can find a capital N belongs to natural numbers such that whenever a small n is greater than or equal to capital N, modulus of an minus L is strictly less than epsilon. So we can just explain what these terms are, and usually this epsilon is called as tolerance or available error. Okay. So let's just discuss what it is meaning to. Okay. So this means that given a value epsilon greater than 0, if we can find a corresponding value n such that whenever a small n is greater than or equal to n, this L, the value which we want to make the limit of the sequence. So this L will be sitting inside an minus epsilon and an plus epsilon, or rather this is L belonging to the open interval an minus epsilon comma an plus epsilon. That's what it is meaning. Or in other case, if for every epsilon, we said that given epsilon greater than 0. So whenever you are given an epsilon, you have to give me an n. So if for every epsilon the above is possible, this will imply that L is the limit of the sequence an. That's what which is being said here. So you can think about the same as a game. Okay, call it the epsilon capital N game. So here epsilon capital N game. Okay. So given any epsilon greater than 0. Okay. Find a corresponding n belongs to n such that whenever small n is greater than or equal to n, this L is lying strictly inside an minus epsilon and an plus epsilon. That is, you can just subtract an from all the terms. So you get minus epsilon strictly less than L minus an strictly less than epsilon. That is, this is nothing but modulus of L minus an, which is nothing but modulus of an minus L is strictly less than epsilon. So this means this, right? So if this condition is being satisfied, then we say that L is the limit of the sequence an. So that's what how to keep the definition. You can just think about the epsilon n game. So given an epsilon, you have to find an n, right? So if we can find for every epsilon such an n, then we say that L is the limit of the sequence A. So let's understand the same by using the next question. Prove that limit n tends to infinity 1 by n is equal to 0 using the epsilon n definition. We know that 1 by n, the sequence 1 by n is approaching 0, right? 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by 8. It is moving closer and closer to 0. So we know that the limit is 0, right? So here we have to use the definition epsilon n gain, that definition. So here let let us call that an is equal to 1 by n, and here we have to show that 0 is the limit, so let L is equal to 0, right? So take an epsilon greater than 0. Okay, so whenever we are taking an epsilon greater than 0, we have to find a capital N, that is a gain. So you give me an epsilon, I will find an n, or I give you an epsilon, you will find an n, that is a gain, right? So we are choosing an arbitrary epsilon greater than 0. So our aim is to find a capital N such that whenever small n is greater than or equal to n, modulus of an minus L is strictly less than epsilon. That is, modulus of 1 by n minus 0 is strictly less than epsilon because an is equal to 1 by n and L is equal to 0 in our question. So this means that modulus of 1 by n is strictly less than epsilon. N is a natural number, so no need of modulus. That will be definitely positive. So that is 1 by n is strictly less than epsilon. So we have to find a capital N such that this happens always. So that is our aim. We have to find that. Find. So what we do is we just assume that suppose if such a capital N exists, okay, and we know that if it exists, whenever small n is greater than or equal to capital N, we have just simplified what we wanted, right? We will have 1 by n is strictly less than epsilon, right? So since this n is greater than or equal to capital N, we will have 1 by n is less than or equal to 1 by capital N, because whenever we are using when we are using reciprocals, the inequality will change to the opposite, right? So here you have 1 by n is less than or equal to 1 by capital N. So suppose if we choose an n, so suppose if we choose an n such that 1 by capital N is strictly less than epsilon. Suppose if this is, if we choose such a capital N, then of course we can choose such a capital N given any epsilon. Okay, that is, suppose you are given epsilon is equal to 10, so you can find 1 by 2. Suppose you are given 9, you can choose 1 by 4, like that. So you can choose for any epsilon, you can choose an n. That is always possible. So then what happens is, then automatically we get 1 by small n is less than or equal to 1 by capital N, which is strictly less than epsilon, right? So what we need is, we have to choose a capital N. We have to choose a capital N such that 1 by capital N is strictly less than epsilon. If we do so, we will end up in what getting what we want. So given an epsilon greater than 0, we get modulus of 1 by n minus 0 strictly less than epsilon whenever n greater than or equal to capital N. Just choose capital N, which is capital N belongs to the natural numbers such that 1 by capital N is strictly less than epsilon. So this is how we end up with that. question. Okay, so you get by the epsilon n definition, you get limit n tends to infinity, 1 by n is equal to 0. Now, note that if limit n tends to infinity, n by n plus 1 is given, then limit n tends to infinity, n by n plus 1 can be written as limit n tends to infinity, n divided by n into 1 plus 1 by n. So, you can cancel n and n. And what you have to do is apply the limit. So you have 1 by 1 plus this 1 by n will go to 0. So you have 1 by 1 plus 0, that is equal to 1. Okay, so that is a note. We can use this technique for finding limits. So find in this question A, find limit n tends to infinity n square plus 1 by 3n square plus n. So you look at the numerator and denominator and check what is the maximum degree that is coming. You can understand that here both of them are having the maximum degree to be 2. So what you do is you take the n square, the term with the maximum degree out. Okay. So limit n tends to infinity n square plus 1 by 3 n square plus n is replaced as limit n tends to infinity n square into 1 plus 1 by n square divided by n square into 3 plus 1 by n. Okay, you can cancel out the n and n. Then limit n tends to infinity, limit n tends to infinity, 1 plus 1 by n square divided by 3 plus 1 by n is what we obtain. And the property of limit, limit of a by b is equal to limit of a by limit of b. So this is equal to limit of n tends to infinity 1 plus 1 by n square divided by limit n tends to infinity 3 plus 1 by n. So when you apply the limits on the numerator, you get that to be equal to, on the numerator 1 plus 0, and at the denominator you get 3 plus 0. So you get at the end 1 by 3 to be the answer, and that is the limit we get. Now B, find limit n tends to infinity 1 minus 3 by n plus n by n plus 1. So limit n tends to infinity 1 minus 3 by n plus n by n plus 1 is equal to limit n tends to infinity 1 minus limit n tends to infinity 3 by n plus limit n tends to infinity n by n plus 1, that is equal to 1 minus this limit will be 0 plus limit n tends to infinity, you just take n out from the denominator, right? So you can cancel n and n, and that you get 1 minus 0 plus applying the limits 1 by 1 plus 0, that is equal to 1 plus 1. So 2 is the limit of this sequence. Now, the next question is, using the A part, using numerical calculations, guess the value of limit n tends to infinity, nth root of n. That is limit n tends to infinity, n raised to 1 by n. Both are the same, okay. And in the B part, we have to use L'Hopital's rule to verify the result we get in A, okay. So, in the A part, we have to definitely use a calculator. So, you can see the table. When n is equal to 1, you get an is equal to 1. That is the first term, a1 is equal to 1 raised to 1 by 1. That is 1. And then you can calculate a5, the fifth term. So, that will be 1.37973. No, then you can calculate using the calculator A10, that will be 1.25893, and you can see A50, A100, A500, A1000, A5000, A10,000 written in the tabular form. And you can infer from this that all of them, as we move forward, all of the values we obtain are moving closer and closer to what the value 1, right? So that is something which we get from this table, and we can guess that the limit is 1. Okay, so that's what we do in the A part. And then we have to verify that our guessing is correct, right? So you have to use the method of L'Hopital's rule as they have said. Limit n tends to infinity, n raised to 1 by n is to be calculated. We have to show that it is 1. So this is equal to, note that e raised to log x is equal to x. This is the property of exponential function. So you have to keep that in mind. This one. Okay, we are going to use that here. So here you have limit n tends to infinity. Instead of n raised to 1 by n, we are going to write e raised to log n raised to 1 by n. So that will be nothing but n raised to 1 by n, right, using this property. And the property of log n raised to 1 by n can be written as 1 by n log n, right? And 1 by n log n is nothing but log n by n. So here you got limit n tends to infinity e raised to log n by n. And what we usually do is apply limits where n is coming, right? So e raised to limit n tends to infinity log n by n. And log n by n, when we apply infinity, we understand that that is in the form infinity by infinity. So we can apply L'Hopital's rule. How? Limit n tends to infinity log n by n is equal to limit n tends to infinity derivative of the numerator divided by derivative of the denominator. So limit n tends to infinity dy dx of log n by dy dx of n. So you get limit n tends to infinity 1 by n by n. So that's how we obtain this. Okay. And that is equal to limit exponential raised to limit n tends to infinity 1 by n square. And we know that limit n tends to infinity 1 by n square will go to 0. So you have e power 0, that is equal to 1. So you got limit n tends to infinity n raised to n raised to 1 by n is equal to 1. So our guessing was right in the A part. So that's that question. So you have a note. Limit n tends to infinity 1 by 10 raised to n is equal to 0. This is an obvious limit of the sequence. If we rewrite it, we know that that is equal to limit n tends to infinity 1 by 10 the whole raised to n. We know that that is equal to 0, right? So here note that this 1 by 10 is strictly less than 1. So we are going to say a theorem which is limits of powers, and it is a very useful result, and we will prove the same. So the theorem says that limit n tends to infinity r raised to n is equal to infinity if r strictly greater than 1, equal to 1 if r is equal to 1, equal to 0 if r is happening inside 0 and 1. Okay. So as the first case, let r is strictly greater than 1. So let's assume r is equal to s plus 1, where s is strictly greater than 0. Then automatically r becomes strictly greater than 1, right? So you can assume like that. Now r raised to n is replaced with s plus 1 raised to n. Using binomial expansion, you get this to be equal to nc0 s raised to 0 plus nc1 s raised to 1 plus nc2 s raised to 2 plus etc. plus ncn s raised to n. So that is equal to 1 plus ns, nc1 is ns, plus nc2 square plus etc. plus ncn is 1. So you get plus etc. plus s raised to n. And all of these terms inside the braces are positive terms because s is strictly greater than 0. We have assumed like that, s is strictly greater than 0. So all of the terms sitting inside this braces will be positive. So you can, if we take r is to n minus 1 plus ns, that will be definitely greater than or equal to 0 because all these terms are positive. Right. So this is because r raised to n minus 1 plus ns is equal to nc2 s square plus etc. plus s power n, which are all positive. So you get r raised to n minus 1 plus ns is greater than or equal to 0. So r power n is greater than or equal to 1 plus ns. Now you apply limits. So you get limit n tends to infinity r raised to n is greater than or equal to limit n tends to infinity 1 plus ns. This limit 1 plus ns, you know that here the n is coming here. So definitely this will go to infinity. So limit n tends to infinity r raised to n is greater than or equal to infinity. Greater than or equal to infinity will mean that is equal to infinity. So limit n tends to infinity, r power n is equal to infinity. So we have proved this. This is done. Okay. Now we have case 2 where r is equal to 1. So case 2, r is equal to 1. So then r power n is equal to 1 for every n belongs to n. So limit n tends to infinity, r power n is equal to limit n tends to infinity 1, which is equal to 1. So we have proved the second case, which is here. And the third cases are ranging from 0 to 1. So here 0 less than or equal to r less than 1, right? So we are just excluding the case r is equal to 0. Just think about 0 strictly less than r strictly less than 1. Say. So this will mean 1 by r is, since r is strictly less than 1, 1 by r is strictly greater than 1. So we have taken exclude the case r is equal to 0 because we have to take 1 by r here. Here r is not equal to 0, so it's okay. Okay. So that is a definite number. So 1 by r is strictly greater than 1. So just assume rho is equal to 1 by r. Okay. Since 1 by r is strictly greater than 1, rho will be strictly greater than 1. Okay. Now limit n tends to infinity, rho power n will be infinity as rho is strictly greater than 1, and this happens because of case 1. We have proved case 1. So this is true. Now limit n tends to infinity, r raised to n is equal to limit n tends to infinity, r is equal to 1 by rho. So limit n tends to infinity, 1 by rho the whole raised to n, and that is equal to 0. Right. So we obtained case 3 also. And let's evaluate some limits using this the theorem the limits of powers. Evaluate a limit n tends to infinity 3 raised to n, limit n tends to infinity e raised to minus n, limit n tends to infinity e plus 2 by 3 raised to n the whole raised to 4. Okay. So first question A, here r is taken to be 3 and 3 is strictly greater than 1. So using the limits of powers, the theorem we just mentioned, we get limit n tends to infinity 3 raised to n is equal to infinity. Now you have here e power minus n, right? So e power minus n is nothing but 1 by e raised to n, which is nothing but 1 by e the whole raised to n. So here we have to take r is equal to 1 by e. Okay, e you have the value to be 2.71828 etc. So this is r is equal to 1 by 2.718 etc. And that will be definitely less than, strictly less than 1. Okay. So by uh, the limits of powers, you get limit n tends to infinity e raised to minus n is equal to 0. Now for the C part, limit n tends to infinity e plus 2 by 3 the whole raised to n the whole raised to 4 is equal to, because this e doesn't have any n, you can take the limit inside. So you get e plus limit n tends to infinity 2 by 3 the whole raised to n the whole raised to 4. Okay. So this 2 by 3 is strictly less than 1. So using the limits of powers rule, you get this to be equal to e plus this becomes 0. Okay, this value becomes 0. So that becoming 0 will imply the value of this limit to be equal to e raised to 4. Now we will move on to comparison test. This is an important test which we can use for solving limits. So suppose if limit n tends to infinity, an is equal to 0 and modulus bn is less than or equal to modulus an. Okay. Then the limit of bn as n tends to infinity will be equal to 0. So you have two sequences an and bn. You know that the limit value of the sequence an is 0 and you can write modulus of bn to be less than or equal to modulus of an. So then automatically we get the implication that the limit of the sequence bn equal to 0. Okay. So we can use this comparison test to find the limits of the next questions. So here in the question A part, you are asked to find limit n tends to infinity sin n by n. The second one is limit n tends to infinity minus 1 raised to n plus n by n. Okay, so to find limit n tends to infinity sin n by n, that is the first question. So here we will choose an to be 1 by n. Okay. We know that limit n tends to infinity an, which is equal to limit n tends to infinity 1 by n is equal to 0. You are aware about that. Now choose bn to be the given sequence sin n by n. Then we know that modulus of bn, which is equal to modulus of sin n by n, which is equal to modulus of sin n by n, because n is always positive, and sin n, the variation will be modulus of sin n will be less than or equal to 1. So you can write this to be less than or equal to modulus of 1 by n, which is equal to modulus of an. So here you have modulus of bn is less than or equal to modulus of an coming, and you know that limit n tends to infinity an is equal to 0. So you can use a comparison test to get limit n tends to infinity bn is equal to limit n tends to infinity sin n by n, that is equal to 0. So you obtained that limit using comparison test. So let's move to the second question. Limit n tends to infinity minus 1 raised to n by n plus n by n. So you just make them into fractions, dividing n on each of the terms in the numerator. So you get limit n tends to infinity minus 1 raised to n by n plus n by n, that is 1. Then limit can be limit of a plus b is equal to limit of a plus limit of b. So you get limit n tends to infinity minus 1 raised to n by n plus limit n tends to infinity 1. That is definitely 1. So you have one limit uh, to find out plus 1. So you have limit n tends to infinity minus 1 raised to n by n plus 1. So we are going to use the comparison test on this term. Okay. So let an is equal to 1 by n here. Limit n tends to infinity an, which is equal to limit n tends to infinity 1 by n is equal to 0, as we know, as we are aware about. Now take bn is equal to bn is equal to minus 1 raised to n by n. Then modulus of bn is equal to modulus of uh, minus 1 raised to n by n, which is less than or equal to 1 by n. So you can write modulus here and modulus here. So you get modulus of bn is less than or equal to modulus of an, and limit n tends to infinity an is equal to 0. So you can use the comparison test, and we can end our the process of using the comparison test by saying limit n tends to infinity bn, that is minus 1 raised to n by n is equal to 0. We have not yet finished. We have to add what we obtained, right, to get the final answer. So limit n tends to infinity minus 1 raised to n plus n by n is equal to 0. You obtained a 0 here, and 1 we had already obtained. So 0 plus 1, that is equal to 0. So that's all about limits of sequences. Thank you for watching this video.